So we're here to talk about SPDM for Storage Binding Specification. My name is Jeff Hilland. I'm a distinguished technologist at Hewlitt Packard Labs. I'm also president of the DMTF and one of the founders of Redfish and co-chair of the SPDM Working Group along with Brett. Brett, you want to introduce yourself?
Sure. I'm Brett Henning. I'm from Broadcom, and as Jeff said, I'm one of the co-chairs of SPDM.
You know, SPDM is an interesting working group. You get to work with some of the brightest and best people. It's absolutely an enjoyable amount of things that go on in that group. Just a disclaimer, the spec we're talking about isn't done yet. It isn't baked. It's out for comments if you want to comment on it. But some of the stuff may change, and perhaps profoundly. So, just most of y'all probably already know this. Why platform security in the first place? Most of these attack vectors that you see here, they're very real. They've happened in the industry, whether it's counterfeit parts or somebody's fake firmware or somebody intercepts snooping and probing or whatever in the industry. There's a lot of different attacks that go on. And what we tried to do with SPDM was to invent something that could expand the root of trust of a platform to all of the devices. So, you know, you got a TPM, you got a BMC, you've got something inside of that machine that has a root of trust in it. How do you then take that and expand and learn to trust everything in the ecosystem before you even power on the server, before you let things go? You know, it's nice to have security in the OS, but if the platform itself isn't secure, you know, how do you trust the machine at all? And we ran into a problem. Some of the, you know, traditional DMTF protocols worked pretty good as far as, you know, MCTP to individual devices. But when it came to the storage world, well, that's just a completely different animal than talking to a power supply or a fan or a NIC. So what we were trying to do with SPDM was really create a common security protocol and data model solution that could work on the control plane, which is all of those wonderful things that the BMC does, as well as the data plane, right? The things going across PCI, and therefore SAS and SATA and all the other data transfer mechanisms that are out there. If you're a device vendor, you really only want one solution, right? If your manageability information is used in one security protocol, you don't want a separate set of gates and a separate set of firmware and a separate set of everything else to take care of your data plane. So, we also, DMTF has published a thing called libSPDM. You can go out there, github.org/DMTF/libSPDM, and it's an open source version of SPDM. It's up to 1.3. We've already published or 1.2. We've already published the 1.3 spec. They're working on it now and should finish either sometime later this year or sometime in the first quarter. So having that open source implementation helps us not only validate the specification, but, you know, code and implementation. And we're trying to make it good enough for you to leverage in your own products. If it's not, please help us improve the quality of the code that's out there. So SPDM overall goals, really, you know, it's the same thing. We started out just trying to attest to the device. Is the device what it says it is? And then try and do secure communication. Do the key exchange that sets up that ability to encrypt data in flight, be it over, you know, PCI uses a CXL, uses SPDM, but so does the management plane as well. So you can encrypt things over I2C, I3C, or USB. Attest various aspects of the device. You know, a lot of people ask us, why don't you just use TLS? Well, TLS won't go out there and measure the workload that's running at the other end. It won't measure your configuration settings. There's no method to do that. Not only that, TLS is designed for, you know, thousands, tens of thousands of connections a second, not some little very small reduced number of gates that's not a Xeon processor or something like that. So. But the ability to go out there and ensure the firmware integrity and device identity is out there. And then again, secure communication over any transport, be it a fabric or just I2C wires. We've been working on SPDM for about 5 years now. You know, we started out with the first version, just device attestation and measurements, and that was it. And the second version, we added key exchange, right? We knew we had to have the ability to do secure sessions, especially if you want to do secure communication over the data plane. We did mutual authentication. and that was put in for some specific folks. Then everybody had a different way of installing their certificates in the factory. That makes it hard to build something that's easy to implement. So we started doing installation of certificates, not only your root cert, but any other certs to help supply chain. We added alias certs, which is our nice way of saying TPM support. And then large message chunking. So it turns out some of our messages were getting a little large, particularly if you're trying to set a cert chain. We put a chunking mechanism in there for get cert, but we didn't want to add that to every command, especially because we have OEM fields and some of that was getting large too. So we put in a generic chunking mechanism. Added SM2, SM3, SM4 for mostly for China. New OIDs were added, which to help identify the use and purpose of the certs. And then in version 1.3, which is the current version that's out right now, we added eventing, multi-key, generic certs. Mel and Hem is the measurement event log and the hash extended measurements. It's a way of finding out what's changing in the system as it's changing so that you can keep up with firmware changes or setting changes or anything along those lines. And then endpoint info was added to identify that end device. We have ways to do that in MCTP, but not every endpoint is MCTP. You don't necessarily know all the information about what's at the other end of the wire. And so we added that. We've been working on a lot of bindings. We're not the only people that do bindings. We did obviously one for MCTP because that's what goes over ITC and how the management plane works inside of a server. And we added the secured messages over MCTP. And then we added secure messages to SPDM binding, and that's the one we if you're wanting to do encrypted traffic like PCI or CXL, that's the spec you referenced there, so that we've got a common framework, actually a common frame on the wire for the SPDM messages and for your encrypted data. And then we added bindings, and one of them is TCP, there was a talk yesterday. If you missed that, you can go back and listen to the recordings when you get home. And then we're working on the SPDM for storage as well. And without further ado, Brett?
All right, thank you. So, I wanted to get into some details of the storage binding. So, first of all, just why did we do this? Well, the big motivator was really just to extend SPDM out to all the devices that are attached to storage interfaces. And this could be SAS, SATA, NVMe, right? There's three primary transports out there, and we really wanted to extend SPDM to all of them. We know that NVMe devices are attached to PCIe. They have routes to get SPDM information to some verifier. Really, none of the other protocols have great routes to support this. There's also just a desire to bring storage systems into the fold on security. Jeff went through a typical view of a system and the number of devices that you'll see and all the different threats against them. One of the things that people kept pointing out to us was storage devices, depending on the use case of the server, they can be 1/3 to 2/3 of the firmware-based devices in a system, and they were all just excluded. So we really wanted to bring them into the fold and make them attestable. There's also just a desire to make it consistent, and this is where we got a lot of the feedback that pushed us to just say make it uniform across all transports so it's available to everybody, so just make it consistent so that you can have common upper layer software. One of the other things that we really wanted to take into account was all the different attachment methods. So devices could be behind fabric controllers. It might be directly attached to the root complex. They might be attached to a storage controller that sits in the middle. So we really needed some kind of implementation that could handle all these different use cases and, again, make it consistent. So what do? We created a new binding spec. In DMTF speak, this spec is referred to as DSP 286, and this binds SPDM to SAS, SATA, and NVMe. one thing to make clear though, this is a binding for SPDM. We did not go out and try to do all of MCTP and put, all of MCTP onto the storage transports. It is just SPDM. And really there were already storage solutions that you all are probably pretty familiar with that, they already handle things like firmware updates and telemetry and all that. It's really just the need was for SPDM. For those who are familiar with SPDM, what we're doing with this binding is basically taking on the role of the 275 spec, so that's the SPDM to MCTP binding, and the 276 spec, which enables secure messages. So we're doing both. We're enabling both types of messages over storage. Where this work is, so right now there's a work in progress available. There's a link on the slides. So you can go out to the DMTF website, you can get a work in progress version of the spec and go through it. It's roughly about a 0.8 maturity, so it's fairly mature, but we're definitely looking for feedback on it. And we'll have a slide that tells you how to send us feedback. So the command flow, I just wanted to spend a couple minutes on this. For those who are familiar with storage, there are certain things you have to do in the storage world that are just based on the way storage works. One is traffic always flows from the initiator, right? It always starts with the initiator, always goes to the device. This isn't like MCTP where a device can just start firing off packets. So one of the things that will look very familiar to people with a storage background, but look a little weird to people from a management background is this command flow. So you'll see with this, what we actually have to do is we have to chain together a couple of commands. So with classic SPDM, what we have here is a digest message. And so all you really have to do with a digest message is you send get digest and the device sends back the response. And it's that easy. It's not that easy in storage. So what we have to do with storage is you actually send an IF send, which carries the request. And then the device just sends back a response that basically says, hey, I got your message, so I have it now. And then the initiator has to turn back around and send an IF receive that provides a buffer to retrieve the response data. So it's this two-stage process. When you go through the spec, you'll definitely see this spelled out. What do the operations look like? So all this runs inside the security protocol commands, or IF send and IF receive for shorthand. In the security protocol commands, there's a 2-byte field that's protocol specific. We're actually using that 2-byte field to just basically form the basis of the binding. And so this gives us a place to put connection IDs. You can think of connection IDs as kind of separate messaging state machines between the initiator and the device. So you can have up to 4 of these state machines running at any time. And that just allows multiple initiating entities, maybe a user on a host as well as a firmware entity on a controller, right? You can have different connections running, so different message sequences running at the same time, and everybody can keep track of it using this connection ID. Multiple connection IDs are optional in the spec. You really only need to, mandatory to support 1, but you're allowed up to 4. And then we also have an SPDM operation. So we set aside a 6-bit field for this. Right now there's only 4 defined, and you can go through the spec to get the details of them. So we also had to come up with a way to do the secured messages format. So again, it looks a little bit different than the SPDM over MCTP approach to this, but there are some reasons for that. Basically, what we ended up having to do is we had to take everything that might be in multiple layers of a message, and they all had to get packed into one buffer. And so then we needed a way to actually make sense of that buffer. So what we ended up coming up with was basically a descriptor format, which, again, very common in the storage world. So the buffer always starts off with a descriptor that's going to tell you the contents of what you have in this buffer. And then that buffer can hold a secured message. And what we mean by a secured message is this is a message that is encrypted and has a message authentication code to protect it. This is all based on TLS, so when the packets are actually in flight, it looks a lot like TLS, just lighter weight to set up. This mechanism can carry SPDM messages. That's its primary use case, is to actually carry SPDM messages in a secure session, but it can carry other IOs as well. So there are ways to put, say, SCSI IOs inside of this message. There's some rules on it, and the spec gets into all the rules. And one thing that we do want to make clear is this is not intended for disk IO. There are no optimizations in here for your actual read-write IO flow. This is really just meant for management, or the control plane, as Jeff was saying. So, all right, what do we need? So, first thing we need is just understand what SPDM means to your ecosystem. So, at this point, it's been, 5 years that SPDM has been available to folks building out the server chassis. It's now being extended out to storage. We want to make sure everyone has a heads up that this is coming, and you need to start understanding what it's going to mean. We need device vendors to start implementing SPDM, specifically on the drive side and on the storage controller side. And then how can the storage project help? Well, there's a few things. So first is, right now we have our work in progress version out, right? This is the thing that will feed into the 1.0 version. So your time to make an impact on 1.0 is right now. So go follow the download link, look at the spec, send us feedback. If you're a member of DMTF, you can obviously work directly with the work group to submit feedback. Otherwise, there's a feedback portal. And then, something that I know that the storage group is starting to look at, specifically the OCP storage group, is starting to look at requirements around SPDM. So now that there's a mechanism to do this, the expectation is that at some point there will be device requirements coming that basically say, hey, you now have to use SPDM, and you have to use it at this level in this way and all these things. So be prepared, and definitely we're ready to work with the storage project on any requirements. So that is it, and I know we have a couple minutes for questions here. Yeah.
Hi guys, David Black from Dell. Want to thank you first of all for mentioning NVMe Fabric. This is definitely of interest. But for NVMe SSDs, I wonder whether you're creating an example. The best thing about standards being that there are so many to choose from.
Yes.
I already know of 3 ways to speak SPDM to a PCI SSD, and depending on how you count, I think you have added at least 2 more, possibly more than that. What do you suggest the industry do to avoid going off in multiple different directions?
Well, that's a good question. That's been a topic of debate, is whether it makes sense to extend to direct attach NVMe for the exact reason you mentioned. Ultimately, the thing that motivated extending it was, first of all the commands are there. It just, there really isn't anything to block it from being extended. And then the goal was really to just give one uniform way of doing SPDM. I think that at the end of the day, it's going to be groups like this that actually sort out, what are we going to do with all this? And yeah, so I think there's more hammering to come.
I'll leave you with the glass half empty response. Just because you can doesn't mean you should.
you know, DMTF writes a lot of specs, right? And a lot of those commands and different specs are, you know, they're optional. They've got options in them. There's probably 20 ways to solve any problem with any set of standards. And that's really where we look to OCP, right? Is everyone else is a descriptive standard, and John Leung, the Hardware Management Incubator Committee rep, calls it, well, those standards bodies are descriptive and OCP is proscriptive. You know, writing the storage requirement specs in the OCP storage group and say, you know, thou shalt do security this way, one way. I think that's what we're looking for.
Can I have one question? So I didn't quite really understand what is the biggest motivation of why we need specific storage binding to SPDM when we have already have MCTP and PCI other mechanism.
Sure. So the control plane inside of a server is you know, there's I2C, I3C, and USB signals going, and we've got the mapping there for MCTP. If you've got like a RAID controller, that signal stops there and doesn't go further on down to the device. Or if you're building a JBOD, that attestation doesn't go past the controller. So, you know, SPDM is designed to be not subject to man and the entity in the middle attacks, right? So you could, in theory, from the BMC tunnel through a controller and go straight to the device, or the controller could be your proxy. Both architectures are there. But the I2C signals aren't running all the way to the drive. And so the BMC can't get to everything. So we've got to go over the data plane to attest all of the drives on SAS and SATA. All right, thank you.